Hey, all and fans and followers, I presume your beloved ones are fine and dandy. It is social activist come good-hearted preacher Professor Resh back with absolute delight for my 112th video on unveil of publication on YouTube today, 20th November 2020, Friday. The topic for today is tidal waves versus tsunamis. Causes and effects. The tsunami, pronounced tsunami is a natural phenomenon consisting of a series of waves generated when water in a lake or sea is rapidly displaced on a massive scale. The earthquakes, landslides, volcanic eruptions, and large meteorite impacts all have the potential to generate a tsunami. The effects of a tsunami can range from unnoticeable to devastating. The term tsunami comes from the Japanese language meaning harbor, tsu and wave, nami. Although in Japanese, tsunami is used for both the singular and plural, in English, tsunamis is well established as a plural. The term was created by fishermen who returned to find a port area surrounding the harbor devastated, although they had not been aware of any wave in the open water. The tsunami is not a subsurface event in the deep ocean. It simply has much smaller amplitude, wave heights offshore, and a very long wavelength, often hundreds of kilometers long, which is why they generally pass unnoticed at sea, forming only a passing hump in the ocean. Tsunamis have been historically referred to as tidal waves because as they approach the land, they take on the characteristics of a violent onrushing tide rather than the sort of cresting waves that are formed by wind action upon the ocean. However, since they are not actually related to tides, the term is considered misleading and its usage is discouraged by oceanographers. A tsunami can be generated by any disturbance that rapidly displaces a large mass of water, such as an earthquake, volcanic eruption, a landslide, or meteorite impact. However, the most common cause is an undersea earthquake. An earthquake which is too small to create a tsunami by itself may trigger an undersea landslide quite capable of generating a tsunami. Tsunamis can be generated when the sea floor abruptly deforms and vertically displaces the overlying water. Such large vertical movements of the Earth's crust can occur at plate boundaries. Subduction earthquakes are particularly effective in generating tsunamis and occur at denser oceanic plates slip under continental plates in a process known as subduction. Submarine landslides, which are sometimes triggered by large earthquakes, as well as collapse of volcanic edifices, may also disturb the overlying water column as sediment and rocks slide downslope and are redistributed across the seafloor. Similarly, a violent submarine volcanic eruption can uplift the water column and form a tsunami. Waves are formed as a displaced water mass moves under the influence of gravity to regain its equilibrium and radiates across the ocean like ripples on a pond. In the 1950s, it was discovered that larger tsunamis than previously believed possible could be caused by landslides, explosive volcanic action, and impact events. These phenomena rapidly displace large volumes of water as energy from falling debris or expansion is transferred to the water into which the debris falls. Tsunamis caused by these mechanisms, unlike the ocean-wide tsunamis caused by some earthquakes, generally dissipate quickly and rarely affect the coastlines distant from the source due to the small area of sea affected. These events can give rise to a much larger local shock wave solitons, such as a landslide at the head of the Ituea Bay, which produced water wave estimated at 50 to 150 meters and reached 524 meters up local mountains. However, an extremely large landslide could generate a mega tsunami that might even have ocean-wide impacts. There is a common misconception that tsunamis behave like wind-driven waves or stress. In fact, a tsunami is better understood as a new and suddenly higher sea level which manifests as a shell or shells of water. The leading edge of a tsunami superficially resembles a breaking wave, but it behaves differently. The rapid rise in sea level, combined with the weight and pressure of the ocean behind it, has far greater force. Although often referred to as tidal waves, a tsunami does not behave like a tidal wave. It doesn't look like the popular impression of a normal wave, only much bigger. Instead, it looks rather like an endlessly onrushing tide which forces its way around and through any obstacle. Most of the damage is caused by the huge mass of water behind the initial wave front as the height of the sea keeps rising fast and floods powerfully into the coastal area. The sheer weight of water is enough to pulverize objects in its path, often reducing buildings to their foundations and storing exposed ground to the bedrock. Large objects such as ships and boulders can be carried several miles inland before the tsunami subsides. Tsunamis act very differently from typical surf swells. They are phenomena which move the entire depth of the ocean, often several kilometers deep rather than just the surface, so they contain immense energy, propagate at high speeds, and can travel transoceanic distances with a little overall energy loss. A tsunami can cause damage thousands of kilometers from its origin, so there may be several hours between its creation and its impact on the coast, arriving long after the seismic wave generated by the originating event arrives. Although the total of overall loss of energy is small, the total energy is spread over a larger and larger circumference as the wave travels, so the energy per linear meter in the wave decreases as the inverse power of the distance from the source. This is the two-dimensional equivalent of the inverse square law in three dimensions. A single tsunami event may involve a series of waves of varying heights. A set of waves is called a trade. In open water, tsunamis have extremely long periods. The time for the next wave top to pass a point after the previous one, from minutes to hours, and long wavelengths of up to several hundred kilometers. This is very different from typical wind-generated swells on the ocean, which might have a period of about 10 seconds and a wavelength of 150 meters. The actual height of a tsunami wave in open water is often less than 1 meter. This is often practically unnoticeable to people on ships. The energy of a tsunami passes through the entire water column to the seabed, unlike surface waves, which typically reach only down to a depth of 10 meters or so. The wave travels across the ocean at speeds from 500 to 1,000 kilometers per hour, like a jet. As the wave approaches land, the sea shallows and the wave no longer travels as quickly, so it begins to pile up. The wave front becomes steeper and taller, and there is less distance between crests. While a person at the surface of deep water could probably not even notice a tsunami, the wave can increase to a height of 30 meters or more as it coastline and compresses. The steepening process is analogous to the cracking of a tapered whip. As a wave goes down, the width from the handle to tip, the same energy is deposited in less and less material, which then moves more violently as it receives this energy. So it increases the velocity. A wave becomes a shallow water wave when the ratio between the water depth and its wavelength gets very small. And since a tsunami has an extremely large wavelength, hundreds of kilometers, tsunamis act as a shallow water wave even in deep oceanic water. Shallow water waves move at a speed that is equal to the square root of the product of the acceleration of gravity, which is 9.8 meters per second square, and the wave water depth. Tsunamis propagate outwards from the source, so forcing the shallow of affected land masses are usually fairly safe. However, tsunami waves can diffract around land masses, as shown in the Indian Ocean tsunami animation as the waves reach southern Sri Lanka and India. They also need not be symmetrical. Tsunami waves may be much stronger in one direction than another, depending on the nature of the source and the surrounding geography. Local geographic peculiarities can lead to a SEICHE, SEICHE, or standing waves forming, which can amplify the onshore damage. For instance, a tsunami that hit Hawaii on April 1, 1946 had a 15-minute interval between wavefronts. The natural resonant period of Hilo Bay is about 30 minutes. That meant that every second wave was in phase with the motion of Hilo Bay, creating a SEICHE in the day. As a result, the following have at various times been associated with a tsunami. An earthquake may be felt. Large quantities of gas may bubble to the water surface and makes the sea look as if it is boiling. The water in the waves may be unusually hot. The water may smell of rotten eggs, the classic smell of hydrogen sulfide or of petrol or oil. The water may sting the skin. A dangerous thunder of boom may be heard, followed by a roaring noise as of a jet plane or a noise akin to the periodic whoop of a helicopter or a whistling sound. The sea may recede to a considerable distance. A flash of red light might be seen near the horizon. As the wave approaches, the top of the wave may glow red. Tsunamis cannot be prevented or precisely predicted, but there are some warning signs of an impending tsunami, and there are many systems being developed and in use to reduce the damage from tsunamis. In instances where the leading edge of the tsunami wave is its trough, the sea will recede from the coast half of the wave's period before the waves arrive. If the slope is shallow, Its recession can exceed many hundreds of kilometers. People unaware of the danger may remain at the shore due to curiosity or for collecting fish from the exposed seabed. This happened in the 2004 tsunami that happened in the Indian Ocean. People went inside, then they were caught by the second wave, third wave, and all that. No escape. In instances where the leading edge of a tsunami is its first peak, succeeding waves can lead to further flooding. Again, being educated about a tsunami is important to realize that when the water level drops the first time, the danger is not yet over. Same thing is true about cyclones also. Cyclones, there is a eye. When the eye crosses the land, everything will be quieter. So people think the cyclone has crossed. But again, the other half of the cyclone will move into the land. People will be get caught unawares. Okay, in a low-lying coastal area, a strong earthquake is a major warning sign that a tsunami may be produced. Regions with a high risk of tsunamis may use tsunami warning systems to detect tsunamis and warn the general population before the wave reaches land. Tsunamis are very common in Japan. Japan is exposed to all kinds of natural calamities. But in spite of that, they are number one in the world for quality. In some communities on the west coast of the US, which is prone to Pacific Ocean tsunamis, warning signs advise people where to run in the event of incoming tsunami. Computer models can roughly predict tsunami arrival and impact based on the information about the event that triggered and the shape of the seafloor, bathymetry, and coastal land topography. One of the early warnings comes from nearby animals. Animals are much smarter. They say humans have the sixth sense, but animals are much smarter than us in a lot of ways. They can sense earthquakes, they can sense tsunamis, they can sense flooding, they can sense volcano eruptions. We need to learn from them. Actually, they say snakes sense sound waves. Many animals sense danger and flee to higher ground before the water arrives. Some scientists speculate that animals may have the ability to sense subsonic relay waves from earthquake minutes or hours before a tsunami strikes shore. While it is not possible to prevent a tsunami in some particularly tsunami-prone countries, some measures have been taken to reduce the damage caused on shore. Japan has implemented an expensive program of building tsunami walls of up to 4.5 meters, 13.5 foot high in front of populated coastal areas. And some of the plants are very flexible, especially the coconut tree. So when the tsunami strikes, if you hold on to this coconut tree, there is a good probability that it will live. Other localities have built floodgates and channels to redirect the water from incoming tsunamis. However, their effectiveness has been questioned as tsunamis are often higher than the barriers. For instance, the tsunami which hit the island of Hokkaido on July 12, 1993 created waves as much as 30 meters, 100 feet tall, as high as a 10-story building. The effects of a tsunami can be mitigated by natural factors such as tree cover on the shoreline, casuarinas, or what is called as some locations in the path of the 2004 Indian Ocean tsunami escaped almost unscathed as a result of the tsunami's energy being zapped. By a belt of trees such as coconut palms and mangroves. Environmentalists have suggested tree planting along stretches of sea coast which are prone to tsunami risk. While it would take some years for the trees to grow to useful size, such plantations would offer a much cheaper and longer-lasting means of tsunami mitigation than the costly and the environmentally destructive method of erecting artificial barriers. The 2004 Indian Ocean earthquake that had a magnitude 9.0 triggered a series of lethal tsunamis on December 26, 2004. People are not even aware of that in countries like India, Sri Lanka, and all that. It killed over 230,000 people, more than 168,000 in Indonesia alone, making it the deadliest tsunami in recorded history. The tsunami killed people over an area ranging from the immediate vicinity of the quake in Indonesia, Thailand, and the northwestern coast of Malaysia to thousands of kilometers away in Bangladesh, India, Sri Lanka, the Maldives, and even as far as Somalia, Kenya, and Tanzania in Eastern Africa. The disaster prompted a huge worldwide effort to help victims of the tragedy, with hundreds of millions of dollars being raised for disaster relief. Unlike in the Pacific Ocean, there is no organized alert service covering the Indian Ocean. This is in part due to the absence of major tsunami events between 1883, the Krakatoa eruption, which killed 36,000 people, and 2004. In light of the 2004 Indian Ocean tsunami, UNESCO and other world bodies have called for a global tsunami monitoring system. Lack of an established infrastructure within this Indian Ocean region means that any development and reconstruction is subject to internal political influences. Tidal waves are waves created by the gravitational forces of the sun or moon and cause changes in the level of water bodies. The intensity of a changing tide is noticeable only in certain parts where it is high enough. Tidal waves are phenomena seen most at coastal areas. Tidal waves occur daily at a coastal area. Tidal waves or ocean waves are occur periodically and depend on the relative position of the Earth and the Moon. This is the reason why the arrival of the tide differs each day. The height of the tidal wave is determined by the gravitation force exerted by the Moon. Hence, it is highest during new and full phases of the Moon. Full moon and dark, and we call it as Amavasa in Tamil. New and full phases of the moon, that is full moon and no moon, and lowest during the quarter phases of the moon. The coastal areas experience two high and low tides daily. Tsunamis were erroneously referred to as tidal waves in the past, but they are not related to tide formation and can occur in any tidal state. In Japanese, tsunami translates harbor wave, as this phenomenon is seen more commonly seen in the coastal area. In early geographic texts, tsunami was also referred to as seismic sea waves. Tsunamis generally have low amplitude but a high wavelength, as I said before, which can be a few hundred kilometers long. Tsunamis generally go unnoticed but see a prominent in shallow waters of land. That's why the speed picks up, the velocity picks up as the water approaches the land. The height also increases. Tidal waves are caused due to both sun and the moon, but due to the close distance between the Earth and the sun, the effect moon has on tidal waves is much greater than the sun. Tsunamis can be generated by earthquakes, erupting submarine volcanoes, or due to any gas bubble erupting in the sea or ocean. These causes have the potential of creating tsunamis provided it occurs just below the body of water, is of moderate amplitude, or displaces a large volume of water. Tidal waves are a phenomenon seen at most coastal areas. The majority of tsunamis, 80%, occurs in the Pacific Ocean, but can occur in any large body of water if the underlying causes are present. Tidal waves occur on a daily basis in most coastal areas, whereas tsunamis occur as and when there is seismic disturbance in large water bodies. Although tsunamis cannot be accurately predicted, there are some warning signs that can be used to save life. In US, at the federal level, National Oceanic and Atmospheric Administration (NOAA) have improved the ability to detect and forecast tsunamis by expanding the sensor network, specifically the Deep Ocean Assessment and Reporting of Tsunamis (DART) (BOIS). Other federal and state activities to increase tsunami safety include improvements to tsunami hazard and evacuation maps for many coastal communities, vulnerability assessments of some coastal populations in several states, and new efforts to increase public awareness of the hazard and how to respond. Despite these advances, many coastal communities in the US still face challenges in responding to a tsunami that arrives in less than an hour after the triggering event. If the source were so close to show that only minutes are available before the tsunami reaches the coast, the public would need to recognize natural cues, mainly ground shaking from the tsunami triggering earthquake, and how to know to evacuate even without official warnings. If the nearby source earthquake is weak, or if the tsunami takes more than an hour or two to reach the coast, technological tsunami detection and forecasting would give advance warning for the evacuation of coastal areas. A tsunami generated close to the shoreline is known as near field tsunami. The tsunami generated by a source far from the point of impact is referred to as far field tsunami. In general, it takes a large earthquake magnitude greater than 7.0 on the Richter scale to generate a damaging tsunami in the near field, and it takes a great earthquake magnitude greater than 8.0 to generate a damaging tsunami in the far field. Near field tsunamis pose a greater risk for coastal communities because the first phase can move on to shore in minutes, so you don't get much time even to evacuate. Far-field tsunamis will not reach the coast for hours and allow time to issue warning and evacuation notices. In some intermediate cases, a tsunami could hit the coast less than an hour after an event at moderate distance from the coast. In this later case, the earthquake may not be felt strongly, so warnings and evacuation notices will be essential for an effective response. The implications for detection and disaster warning and response are different for near-field and far-field tsunamis. Assessing tsunami risk is challenging. There is a paucity of information about the frequency, source, and characteristics of past tsunamis and the reoccurrence intervals. Vulnerability of coastal communities cannot be assessed without considering interdependence from a larger economic and socio-political context, and the political potential impacts of future events are uncertain. Although difficult to assess, societal response to tsunamis is critical information in the development and prioritization of risk reduction efforts, including education, preparedness planning, warning system development, mitigation, and response strategies at the local, state, and federal level. The level of sophistication, accuracy, resolution, and format required for assessing societal risk to tsunamis will depend on the intended use of the information. A typical tsunami hazard assessment accordingly includes studies on the locations, sizes, and histories of tsunami sources, are usually earthquakes. It can also be landslides or volcanic eruptions. Inundation models, which determine the areas most likely to be flooded. Hazard maps, which portray inundation models, are maps that show roads, elevation, and buildings and other critical infrastructure, and evacuation maps, which depict areas that need to be evacuated in the event of tsunami and show evacuation routes to safe events. Modeling tsunami inundation begins at the tsunami source with estimates of the seafloor deformation that initiates a tsunami. The simulation also requires accurate information on the topography of the seafloor to understand the surface over which tsunami waves propagate. A robust computational model to simulate the formation of tsunami waves. Knowledge of the sizes and recurrence intervals of tsunami triggering events is only now emerging and is improving the understanding of tsunami sources, critical to producing a comprehensive tsunami hazard assessment, but currently no formal procedures for periodic re-evaluation of tsunami risks exist. The accuracy and realism of tsunami inundation models is limited by scientific uncertainties in determining the source of tsunamis, limited spatial resolution of bathymetry, lack of topography data, and difficulties in modeling the complexity of processes that take place when the tsunami wave interacts with the building and natural features of the coast. Modeling efforts would greatly benefit from a rigorous vetting process, peer review, and validation with the field data. Evacuation maps are critical tools for preparing and evacuating the public, educating the public about the hazard and the appropriate response before an impending tsunami. Tsunamis pose risks only if they have the potential to impact people or the things people value. Therefore, a first step in understanding vulnerability is to inventory number and characteristics of individuals in tsunami hazard zones. In addition, emergency managers should assess the demographic characteristics, as these can affect an individual's ability to see, understand, and respond to warning messages. For example, the very young and old may need evacuation assistance and thus have higher sensitivity to tsunami hazards. Currently, there is no national assessment of population exposure and sensitivity to tsunamis, including the number and types of individuals in tsunami hazard zones. This lack of information limits abilities to assess national tsunami risk, develop realistic evacuation plans, and tailor education efforts to at-risk individuals. Surviving a tsunami depends on the ability of an individual in the hazard zone to recognize warning signals, make correct decisions, and act quickly. But normally, in case of an emergency, people panic. For near-field tsunamis, waves will arrive within minutes after generation. Therefore, at-risk individuals will need to recognize natural cues such as the ground shaking or the receding of the water line as a primary warning. Knowledge and readiness gained through pre-event education may save lives. For far-field tsunamis, waves will arise several hours after the generation, and individuals need to understand official warnings and follow instructions given by local agencies. Regardless of the tsunami source, Integrated public education and preparedness planning are necessary to protect lives and to make tsunami knowledge commonplace and ingrained into local culture and folk wisdom. So many events that happen around us naturally are unpredictable but are devastating effects. 21st century computer geeks, also known as idiots, to the core, think computers are a panacea for all problems. In reality, computers and programs developed by these lunatics only cause problems. Hacking, the cyber frauds, simulation and animation fail miserably because basic modeling is screwed up, attributed to relying on misleading or improper data. We are not God to control or contain natural disasters, but emergency preparedness will help us to mitigate the damage. Education of the general public about natural calamities and what to do when it strikes will curtail the damage, especially loss of precious human lives. Government should allot more money on research and development of risk assessment and natural disasters, mitigation measures, emergency preparedness, and creation of overall awareness through appropriate education and training of the general public. Cut down expenditure on destruction, also known as the defense. Spend it wisely on constructively and socially useful projects. Is anybody listening? Debates, discussion on open-ended topics like this can go on forever. Anyhow, let me pull the plug here. We'll meet again real soon with another interesting topic. Some of the statements, views expressed are solely mine based on limited knowledge gained over 6 decades of versatile experience. Always watch these videos with closed caption, subtitles for absolute 100% comprehension as per my sincere recommendation zillion times so far. I know I rushed through to complete the presentation within 20 minutes max, which is a norm that I have set myself to retain the viewer's attention. But I know pretty well that I exceed this time limit. Today I must have taken double the time. This happens when I make honest attempts to cover the selected topic more elaborately, including so many intricate fine details, referring a wide variety of sources, in particular Wikipedia quite extensively, besides other articles and books published recently. Besides, of course, I sprinkle my own salt and pepper and season it with my personal experiences so far in my life and also intuition. Stay at home as much as possible to maintain social distancing attributed to pandemic novel COVID-19 and prolong your lifespan. Lead a healthy life. God alone can put a stop to unnatural events, maybe bio-war and cyber war events like pandemics, which may lead to apocalypse and extinction of all sentient species on Earth for no fault of theirs. Rest in peace and harmony.